Hi, thank you for joining me today for this talk on direct estimation of SAGDable volumes from geological models using oil sands net pay connectivity criteria for ranking and planning. By the end of the talk, this title may make sense. It's quite a long one, and there are a lot of pieces to it. And if you're in the session following this geomodeling session, then you saw the electrofacies talk I just gave. So, and my co-author on this is Sasan Gambari. He did inspire me to present this material as he's been looking at this subject. So I'd like to acknowledge three companies that provide me with technology that I've been using for these kinds of materials in the presentations. Emerson, Geovariances, and Basic Friendly. So in this talk, we're going to cover briefly the SAGD as a base case technology, a little bit on the geologic concepts, modeling, and issues to assess for this topic. For example, the properties, the facies, porosity, permeability, saturation. And we'll discuss bulk oil weight in detail. That's what we're using for our connectivity calculation and net pay criteria for SAGD, which is the main topic. And we'll go over summaries of uses for the model ranking and connectivity measures. Here we have an image of some oil sands. This would be from good reservoir material. It's just unconsolidated sand saturated with bitumen. To extract the bitumen, SAGD has been the base case technology. There are newer technologies that use hybrids of it, but this is the base for the evaluation. The theoretical steam chamber in a homogeneous medium is shown on the left here with a perfect sweep of the bitumen, gravity sweep. When we have mudstone or shale interbeds, irregular steam chambers form as a result of these heterogeneities. This increases the path, the flow links, path links, and that's shown here. So these mud beds can act as barriers, baffles, preventing steam chamber growth, and it can increase pressures locally, creating hot spots or flashing into the producers, which can inhibit the entire well or slot or even a pad at times, areas of pads. So at the top of thick zones, the presence of mud or shale can act as a seal on the reservoir or as cap rock if it's big enough. And for our evaluation, we're going to be looking at around 2 meters of thickness, 1 to 3, and for the width to really impact the steam chamber and connectivity, 25 to 50 meters of horizontal width on these. So understanding reservoir heterogeneities is important to reservoir management and planning. The key here is that only bitumen contacted by steam or high temperatures and able to flow, that is mobilized by gravity, will be recovered. So some of the enhanced methods do reduce the temperature of mobilization, but this is the key point. As well, the startup requires that we have a rather homogeneous reservoir in the vicinity of the injector and producer. The key point on the slide is that the rate of flow out of the producer is directly related to the effective length that is of the horizontal, that is effective being that it's in the pay zone. As well, I just want to draw your attention to the equation involving permeability, porosity, a saturation term, height or thickness of the pay zone, and then it's inversely related to viscosity. So we want to lower viscosity, of course, to increase the flow rate. This is a general diagram on the forecasting roadmap and a subsurface team. We have our concept models. We have some analogous reservoir information. The team is driven by that to make interpretations, do regional or area mapping. We're always looking at the geological and reservoir properties that relate to performance. And this main workflow here is that we build our models, simulate, and get those relationships to predict performance. So we want to use some of these relationships, if we can, to estimate performance. If we look at concepts on the reservoir framework, we can then understand some of the pay and risks that we want to be aware of. So we have our main reservoir zone, the best reservoir, and that's our net pay. We try to put the producer injector as low as possible in that to maximize our recovery. We may have some stranded, narrow bitumen, and at the top we may have some deep zones, either water or gas in contact. We need to know about that. If we have non-reservoir facies at the top of the bitumen, this is good. It acts as a seal. Geomodeling involves concepts to models. We have our analog. Here's a nice outcrop with a massive sand at the base. That drives a concept model, our interpretation of facies here, classifying facies that are related to petrophysics. We've got our seismic for frameworks. Also gives us some tipping information that we conceptually imposed on our model here to study different extraction methods. And then vertical permeability is just one of those parameters that we solve for. Here we have the implementation of the reservoir modeling workflow. We define the project with those concepts, get our data in, set up our structure, stratigraphic framework, zones, and grid, and scale data into those grids. The key here then is the heterogeneity modeling, which is a hierarchical process. It's facies first, followed by other parameters like porosity and permeability. Permeability and porosity are related. Saturation is related to facies, not always one-to-one related to porosity. And then we have our model analysis and post-processing, working with realizations and scenarios. And so we're also going to emphasize that in this talk. Permeability is maybe the most important parameter for flow in the thermal oil sands. There are different methods that can be useful, and we apply them by facies consistent with the facies in the Geo model. And so core analysis can be used, although it does have issues in oil sands. Illustrated here is the linear function, say for mudstone, is steep for low porosity, and for the best reservoir sand, it's flatter for those high porosities. So piecewise, it gives us this nonlinear shape. So this is an adequate model, can get you a long way. This study was looking at textures of the different kinds of lithologies, and it very much showed that nonlinearity on the poro-perm, as well as showed a strong percolation effect with vertical perm. So the vertical perm did not increase very rapidly until we got into the better quality facies. In other words, there's more connections in the vertical direction in the best facies. Water saturation. The key here is that we want to honor vertical trends due to the facies, rock types, grain size variation. And so we have to define a free surface. This is an issue for some of the packages because but we want to model or map a bitumen water or gas water contact surface, something we can map over a larger area. So there's some tricks here, but over a smaller area pad, we might just be able to use TBD as approximate, and that's easy in the geomodeling packages. Not all of them let you flatten a model on an arbitrary surface. But the key here for water saturation modeling is to avoid simulating in the stratigraphic correlation lines in your K layers. This is not physically what water does. It's not all. Okay, so here's just one example presented in 2009 where we look at the sand facies, the best facies, and the saturations in it as a function of elevation over a large area using a flattening surface on the gas contact. And it shows two very clear transition zones. This is a very strong capillary effect. And so we use that in the model. We've got a facies model. We see two zones in there. The porosity is directly related to these lithologies, these facies. But the saturation, we use these trends, and we have lateral variation as well. So the fluid distribution is different than the porosity distribution. We need to make sure we model that as best we can. Here's another example of water saturation and the capillary effect. If we look at saturation as a function of elevation for all facies, all wells, it's just a shotgun blast. So when we separate by facies, by lithology, we have the strong capillary effect illustrated. So this shows a very flat transition for the best sand. For the next quality, reservoir sand, the transition steepens, and then as the sand quality degrades further, it's steeper yet again. So this is very important to have a good lithology model and to model these trends. This slide illustrates the effect of that transition zone, and we have a bimodal water saturation in the good sandy facies. So it's high porosities, and so we have both good quality bitumen and a wet zone. And this is a good reason why modelers should avoid co-simulating water and porosity. Now we introduce bulk oil weight. This is the weight percent of bitumen in a mining unit or rock volume. It's the bitumen weight to the total rock plus fluid weight, and it represents a bitumen ore grade quality. In the end of the 90s, early 2000s, we used this because we found it was highly correlated to the steam energy required to mobilize and produce bitumen. So we're going to use it for our ranking criteria. Going into more detail on bulk oil weight, this is the weight of the bitumen over the sum of the grain weight, the weight of the grains, plus the weight of the oil in the pores, and the weight of the water in the pores. So that's bulk oil weight. And here we have a plot of porosity, of saturation versus porosity. And it's color-coded by the bulk oil weight. So for the SAGD process, 6% is a cutoff. In mining, 7% is used as a grade control cutoff. But for us, it's 6 because that gives us about 50% water saturation and 27% porosity, two good cutoffs to use in the reservoir. And that example of 6% is here on the graph. There is an ambiguity because we could have higher bitumen saturation and lower porosity. So that's something we want to consider. We'll come back to that point later, but that's shown here. A high quality would be, say, 10%, and that's down in this zone. So if we apply a 6% mask of the red samples, that's shown here, 10% is here. Note that we have this, this bimodality here of high porosity and high water, and that's our thief or transition zone showing up there. The porosity for the 10% bulk oil weight cutoff is shown here. For saturation, it's low here, and that's your histogram of bulk oil weight. Okay, so what's the volume we're wanting to look at, and where are we going to put pads, well pairs, and such? So we need to understand these complexities. Connectivity is an important factor in most reservoir studies. Connectivity in clastics, for example, depends on a number of factors here. Also on the depositional system. This just illustrates connections. Why is it important? Because we define it for processing our models. We look at connected volumes and ranking and choosing realizations. It has a practical impact on flow and drainage for flooding and sweeping reservoirs. So it's known that in high net to gross systems, we have a lot of connectivity, but for oil sands, high net to gross, we are in a very high net to gross system, and so conventional connectivity does not represent thermal sweep performance. So here we're going to look at our pay criteria. It's a complicated slide, so let's go through it slowly here. We've got a bulk oil weight column where we want to define the base of continuous bitumen at the top. From that we get the gross and then derive the net. And the last step is to assess the ambiguity. So at the base, we need to start up the SAGD. We have to have a very high quality, 5 to 7 meters. And that gives us a base. We look then for thin. We can ignore thin mud beds. And when we finally get to thicker bulk oil, low bulk oil weight, that's our top. So here we have our top base. That's our gross, and then we remove these non-net sections, and that gives us the net from the gross. So to assess the ambiguity, we look at the vertical perm over a barrier, and I'm giving the example of 150 millidarcies. It could be 125, 175. Just depends on what kind of perm model you have. And the width, 25 to 50 meters. So we're looking at the top of this zone, and when we hit that low bulk oil weight, it's either non-net facies or there's a water zone. So steam could actually rise further. So we're applying this criteria to understand if we have a thief zone at the top, and where the actual top of the steam chamber would be. So that's the last step. So there's a script from Emerson. It actually has two major errors in it, so I don't show this. But the idea here is that you've got your bulk oil weight in your model. From that, calculate gross, and then the net. So these are just binaries, binary images, zeros and ones. So this just identifies your net cells. And so this is what the maps might look like. From, say, P50 maps of these, we could get a probability distribution on volume over potential pad areas and use this for our early phase setting up pads and such. I use it for ranking. In this modeling, we applied dips. From that, we got porosity, saturation, and we also looked at a flatline model. This was really to study different extraction methods. When applying that script, different different application of the script without the some of the problems in it. We have this binary, and that gives us, say, a net continuous bitumen thickness map. We can also get hydrocarbon pore volume for that shape. If we use that flatline model, we'll get a different look. So this could be part of our scenario-based uncertainty. And then finally we get to the direct forecasting. And here we have the idea that we can look over some drainage area, be a slot, pad, and from simulation get the relationship between the geologic factors, descriptive factors, and our performance measures, and get this response surface fit through it. So we run different realizations and scenarios from our ranking to get that response surface. We could use functional proxies like quadratics, or we can use physical proxies. This is just one equation, and that's discussed in this paper. And just another application later in the development phase. This is one from the early 2000s of optimizing the vertical well placement. We had already decided where our pads and slots were, and we just wanted to rank the well pairs to maximize the NPV of the project drill. We had more slots than we were planning to drill up front. So we got a ranking, and that helped us plan for the initial production and staging the development. This can be done early on a paddable level or on the well slot drilling level. So in conclusion, these screening methods are scalable for early stage or late stage decision processes. There are many uses of the 3D model, simulations, and post-processing of the realizations. The geomodeling methods are important. They're critical for representing heterogeneities for facies, saturation, perm, etc. Connectivity is a high impact variable to consider for thermal sweep. It's high impact in a lot of reservoirs. Bulk oil weight is very useful for calculating net pay and connectivity in this columnar scalable method. And oil sands economics and planning is enhanced using these methods. Thank you.